Now we have a small numerical based on the theory we have studied in this chapter. We have a simple statement of the numerical: a steel cylinder 30 centimeter long and 2.5 centimeter in diameter falls due to its own weight at a uniform rate of 10 centimeter per second inside a tube of slightly larger diameter. A lubricating oil film of constant thickness is there between the cylinder and the tube. Determine the clearance between the tube and the cylinder if mu, which is known as coefficient of viscosity, is equal to 0.08 Pascal second. The density of steel is 7600 kg per meter cube. Now, to solve this numerical, what generally we try to do, we convert numerical into a figure, and we try to give as much information as given in the statement of the problem with the help of that figure itself. So, in this figure we have a steel cylinder. This is a steel cylinder going downward with velocity v. This is a steel cylinder going downward with velocity v, and we have a tube here. This is a tube which is fixed on both the sides, and the clearance is also given here, and this clearance may be taken as thickness T, right, and density of the steel is given. So, it is going down because of some force, and what is that force? That force is due to the weight of the cylinder. Because of the weight there is a force F. Now, this force F can be calculated with the help of density of the steel. Density of the steel is given, so we can find out the weight, right. So, we can find out the weight. Now, in this figure, with the help of the knowledge of Newton's viscosity law, we know that this downward force is opposed because of the lubricating oil available in between cylinder and the tube, and that force is applied in upward direction. What is that force? That force is known as a viscous force. So, this viscous force, how do you get viscous force? This viscous force is calculated with the help of our governing principles, which we have studied in this chapter. What is that governing principle? That we know tau. Tau is shear force, shear stress. Tau is equal to mu. Mu is given to us du over dy. Now, how do you get du over dy? Du velocity is given to us. What is velocity? Velocity is 10 centimeter per second. So, velocity is given to us. So, du 10 centimeter per second divided by dy. Dy is distance between the solid surface and the tube, right. So, this is to be calculated, which is taken as T. So, 10 over T in particular unit and multiplied by mu. Mu is also given to us 0.8 Pascal second. So, this will lead to give you tau. Tau is shear stress. Now, tau is equal to mu du over dy. With the help of that we have calculated tau. Now, our aim is to calculate force in upward direction, because under equilibrium condition these force in downward direction, which is due to the weight, and the force in upward direction, which is due to the viscous effects, will be same. So, how do we get force with the help of tau? Tau multiplied by shear area. What is shear area in this case? If this diameter is d, and length of the pipe, length of the cylinder is given 30 centimeter long and 2.5 centimeter in diameter, then shear area will be pi dl. So, shear stress multiplied by pi dl. This will give us shear force. This shear force will be equal to this force F. Now we will have that equation, one equation, solve that equation for the unknown, and we will get the answer of this question. So whenever we try to solve numericals given in a statement form, we try to develop a figure, try to do the nomenclature on that figure, and try to recall the governing principles with the help of those principles, whether it may be the basic principle or the secondary derived equations. Based on that situation, we develop the final formula and put the values in that formula and try to solve for getting the correct answer. So after explaining, it is again written here what I have just explained to you, that this is the way to calculate the force pi by 4 d square pi r square L into G into rho. So volume multiplied by G, weight of the tube cylinder, is equal to pi dl into tau. So tau is taken with the help of Newton's viscosity law, and we solve this equation, and ultimately we will get this answer. That answer is equal to 0.017 mm. So in this manner we have finished this first chapter. It is related to some historical development of the fluid mechanics and some of the application areas of the fluid mechanics and some basic properties of the fluid mechanics, and we discussed one governing relationship that is known as Newton's viscosity law, and we discussed one numerical by using this governing relationship for giving the answer to certain numericals.